So we were looking at the propagation of light, and we had got to the stage of the equation box A minus R AB equals 0, after having said that the vector potential could be expanded in this fashion. So we were looking at what the consequences of the wave equation were, order by order in h bar. So if you look back to the last equation of the previous lecture, to order 1 over h bar squared, you will find, let me remind you that PA, what I call the generalized momentum, is the gradient of theta. So to order 1 over h bar squared, what you discover is that p squared is equal to 0. So that p is a null vector, and that really is what you'd expect for the propagation of light. The next equation that you end up with, to order 1 over h bar, is an equation which tells you how the polarization vector A actually changes as you move along as you move through space-time. So to order 1 over h bar, what you discover is that AA times del B PB plus 2 PB del B AA equals 0. So that one more thing, plus p squared times b. But since p is null, you can forget this part, and this just tells you how A changes as you move it throughout space-time. Now, at first sight, this may look a little bit strange, but if you think about what you have got so far, you have that PA is equal to 0. You might think that just means it's null, but a consequence of P being of the form del A of theta is that if you take the gradient of this thing, so act with del B on it, you'll discover that PA del B PA is equal to 0. That doesn't look like much progress either. But because P is exact, it's a gradient of something, it follows that del B of PA is equal to del A of PB. So substituting this into here gives you PA del A of PB is equal to 0. In other words, it obeys the geodesic equation. So you can think about the interpretation of this in a slightly different way. What this is really saying is it's telling you how you parallelly transport A along the null geodesics generated by P. So I want to concentrate on this last equation, what might be called the equation for the polarization vector. And the simplest thing to do is just to rewrite it in the form PB del B AA is equal to minus a half AA del B PB. That's just motivated by the fact that P obeys the geodesic equation. So what this tells you is precisely what I said. It tells you the parallel transport of A along these null geodesics is given by the divergence of P. Physically, this is not entirely convenient because A, if you think about it, really is the polarization vector of wave. This thing contains two pieces of information. It contains the amplitude and the polarization, and it's convenient to separate those two things out. So A contains information about the amplitude of the wave, and the polarization. If we separate out those two things, which you're free to do, you can write the polarization vector now as an amplitude, A, times a unit vector, epsilon, which I'll take to be a space-like vector, which is the polarization. So I'll call this polarization, being the directional part of it, and this we can call the amplitude. And just as you would do in flat space, you can regard epsilon A as a unit space-like vector. So the thing to do, of course, is to substitute that into the equation, which tells you how A changes as you move along these geodesics. And if you just substitute in, you'll get PB del B of A epsilon A equals minus a half A times epsilon A del B of PB. That doesn't look very deep. Since epsilon is a unit vector, you know that that's true. It's a unit space-like vector. And you also, as a consequence of this, know that epsilon A del B epsilon A is equal to 0, just by differentiating that. That means you can simplify this expression, multiply out this term, you'll get PB del B A times epsilon A plus PB A del B epsilon A is equal to minus a half of A epsilon A del B PB. To get the amplitude equation, all you need to do is multiply this by epsilon A. This first term is just going to give you 1 times PB del B A. So that tells you how the amplitude of the thing changes as you move along these geodesics. This term here will give you epsilon A del B epsilon A, so you get nothing. This term here will give you minus 1/2 of A del B PB. So I think we can call this the amplitude equation. It tells you how the amplitude of the thing changes as you move along the geodesics. Now you get one further thing. Because this is 0, that tells you that that is equal to that. So you end up concluding that this thing has got to be separately equal to 0. So that tells you how the polarization changes as you move along the geodesics. The polarization equation, the polarization is parallelly transported along the geodesics.
This fails if the geodesic isn't null.
It has to be null because we concluded PA is equal to 0. wave equation. So the kind of situation that one is sort of considering here is so what you've really done is you derived the idea of getting geodesics, null geodesics, plus a little bit more information from just the fact that you have Maxwell's equations.
Is there a way in general that you consistently treat a field theory with massive photons?
Massive photons.
Yeah. If the universe is filled with plasma, you'll have an effect on that. So do the photons travel into your d6? Well, clearly they wouldn't.
You can introduce mass terms into the wave equation in a consistent way. That was first done by a chap called Proker. The microscopic origin of his mass term does not correspond to the effects that you're talking about, because introducing a mass term the way he did it would violate what you usually think of as gauge invariance. If you want to do what you're describing, I think you have to introduce a frequency-dependent mass term. It'll all become rather more complicated. I've never seen it done. Usually you wouldn't bother doing this because you would just say, well, plasma effects are sort of rather different to general relativistic effects. And so you'd say, well, geodesics are important on large scales, not on small scales. And so you wouldn't actually probably take account of both things at the same time.
On large scales, you would have no photons. Plasma down.
Well, actually, the people who talk about things like polarization of the cosmic microwave background must have done things like that, actually.
Well, they assume that they're completely freely propagating, so that they actually are masses.
No. No, that can't be right, because prior to decoupling that wasn't true.
No, I mean from decoupling.
Oh, from decoupling, yes, but to start with, they must have taken account of the interactions with matter. So I think people who look at CMB fluctuations must know about this, even if I don't explicitly. So, the kind of situation that one is then considering is things like collections of light rays propagating in space-time. So you can think of these collections of geodesics looking something like this. So these would be null geodesics. And the tangent vectors to each of these things would be p, which you could, if you want, write in the form dx by d lambda or something like that, because you know that p obeys the geodesic equation. Now, one thing that's very useful to do is to consider how these light rays spread out and evolve in time. And a simple way of doing this is just to simply say, well, if you had a whole collection of things like the beam from a flashlight, then you would say, oh, well, the cross-sectional area of this beam is A. And you would trace those rays, and you'd move along to here, something like that. And you, of course, discover that as you changed lambda, moving up these rays, something like that, you'd end up with the area of this thing. So this would be a function of lambda. So it tells you how the beam is going to spread out. So A is the cross-sectional area of some beam. And it will be, of course, a function of lambda. You can work out how that evolves as you move through space-time along the geodesics. But actually it's particularly easy. The easiest way to do it is just simply by energy conservation. Energy is conserved in the beam. And therefore d by d lambda of A times A squared must be 0. A being the amplitude that you find over here. That's because the energy in the beam is proportional to A squared. sometimes it's more useful to rewrite this in a slightly different way and calculate how big A varies as you move along the curve. So another way of writing d by d lambda of AA squared is to say that PA del A of A times A squared is equal to 0. So it's easy to multiply that out. You'll get PA del A of A times A squared plus 2PA del A of A times A equals 0. But this thing here, you already know from the amplitude equation. If you look over here, you'll see PB del B of A. So this term can be replaced just by the divergence of P. So you get that. And so our factors of little a squared all cancel out. So that tells you how the area of this beam behaves as you move along the geodesics. So you can think of this as the area of the beam changes by, well, PA del A of A is equal to the area times the divergence of P.
The energy in the beam doesn't affect the space.
Yes, because that would have to be a hugely intense beam to do that.
But is that just
we assumed that because we looked at just solutions of Maxwell's equations on a fixed space-time background. We did not incorporate the back reaction of the wave on the space-time. That would be a horribly nonlinear problem into which I don't wish to go right now. If you want to do things like that, you can come to a lecture I'm giving on, I think, May the 11th on the subject of singularities in a series of seminars here on what are called big questions. Because I will have to do that there. So, the thing that I want to look at now is what is usually called the focusing equation. This equation is perfectly fine, but it's not in its most useful form. If you look at this picture that we've got over here, you can see that it's a sort of general description of how collections of light rays propagate through space-time. But if you think about black holes, then you already know something about this. So one picture that you draw when it comes to discussing black holes is a picture of the event horizon. So the event horizon consists of null geodesics which just propagate through space-time and look something like that. Here are the light cones, and this is some closed surface that gives rise to a sphere. And of course, it looks something like that. So there are lots of null geodesics which are sitting there. So here is a picture of an event horizon. And the boundary of the event horizon consists of a series of surfaces, like this. You have some parameter lambda which takes you from the past to the future. And at least for static black holes, if you measured the area down here initially and the area up here, you would of course discover that they were the same, because the space-time is static or stationary. And that's precisely the situation that happens in the Kerr-Newman metrics that we've looked at relatively extensively. But of course we might imagine doing something a bit time-dependent. So you could imagine, in fact, when we looked at the first law of black holes, we imagined throwing something in here, some matter, which we just simply throw in. The black hole will settle down to a new configuration after a bit of time, and the area will change. But that area is precisely described by this equation. So what I wanted to do was to find what is usually called the focusing equation, which gives you a rather clear idea of how this area changes as you evolve in space-time. What you need to do is to calculate the second derivative of the square root of the area. At first sight that might seem a little bit perverse, but this is the thing which gives you the easiest calculation to do. So you just simply have to do all the calculations that will get you the answer. So you have to calculate that object. It's not hard, but it's a little bit lengthy. You differentiate this term, and you will get 1/2 PB del B A times A to the minus a half. You stare at that, and you realize that you have seen that before. There is the area equation just up here, and so you can rewrite this in terms of the divergence of P. You'll get 1/2 PA del A of PB del B A is A times the divergence of P, so you'll have A to the plus 1/2 now del B of PB. Now you keep going. You've got two terms here. And you just multiply them out. So the first term is going to give you 1/4 PA del A of A times A to the minus a half del B of PB. The next term comes from the second derivative of P here. That's going to be 1/2 A to the 1/2 del PA del A del B of PB. Now, let's see. You now use the area equation again here to get rid of this term that looks like PA del A of A. So what you'll end up with is 1/4 of A to the 1/2 del A PA del B of PB. So you can now see where this is going to go. This basically tells you the second derivative of something is proportional to A to the 1/2 here and A to the 1/2 here. It's beginning to look like some differential equation that we might be able to cope with. If you look at this thing here, it turns out that it's rather more convenient to swap around some of these p's, because you know that PA del A of PB is going to be equal to 0. That isn't what you've got here, but it's almost what you've got here. So you can get rid of some of this term if you commute these two derivatives. If you do that, you will end up with 1/2 A to the 1/2 PA del B del A PB, and then a term involving the Ricci tensor, PA R A B B C P C. But of course, if you contract the Riemann tensor on its second and third index, you'll end up with minus the Ricci tensor. And so you'll have at this stage (1/4) A to the 1/2 del A PA del B PB plus, from the Ricci tensor term, 1/2 A to the half, a minus sign because it's got the negative sign when you contract there, R A B P A P B, and then the remaining term, which is plus 1/2 A to the 1/2 PA del B del A of PB. That's what I've got, yes. Now I'd like to get rid of this term, so what I need to do is to get this PA inside here. So I can do that at the expense of subtracting off the derivative of P. So you get 1/4 of A to the 1/2 del A PA del B PB minus 1/2 A to the 1/2 RAB PA PB plus 1/2 of R A to the half, and then del B of PA del A PB, and then I have to subtract off a correction term, which is the derivative of that, minus 1/2 A to the 1/2 del B PA times del A of PB. Then you argue that because P is geodesic, you can forget that term. So you end up with that equation. This equation is sometimes called the focusing equation because this thing has got a definite sign. So you end up with d2 by d lambda squared of the square root of A is equal to a term here which is basically a multiple of A to the half. And that's the universal part of the whole thing. Then you have minus 1/2 RAB PA PB. Then you have a term which is of the form that term plus that term. I'm just going to write that as sigma squared. It looks like that is prejudging some issue. Let me write the minus sign up there, because it looks like sigma squared has got definite sign. So sigma squared is just to be this collection of stuff involving the derivatives of P. Explicitly, it's going to be 1/2 del A PB del B PA minus 1/4 del A PA del B PB. Now I hinted this has got definite sign, so let's prove that it's got definite sign. Sigma squared can be rewritten in the following way: 1/2 of del A PB del C PD into GAC, let me get this right, GBD minus 1/2 GAB GCD. Just in case you say, but that's contracted on the first and third index here, but not over here, remember that del A of PB is the same thing as del A del B of theta, which is the same as del B del A of theta, which is the same thing as del B of PA. So I can swap those two things round. It turns out that sigma squared is positive. Let's actually do that calculation to see whether or not this really is positive. Let's first of all look at del A PB and call that XAB. You can represent that as some symmetric matrix. Let's first of all think about doing this in some orthonormal frame. We've got here del P, but here we just have some metrics, so picking an orthonormal frame to look at this in is completely reasonable. Del A PB is XAB. Let's think of some null vector at some point in space. Well, whatever it is going to be of the form something minus something 0, 0 in an orthonormal frame. All you've done is you've chosen the spatial component to be in the x direction if you do that. That will give you a null vector. And you know that PA del A of PB must be equal to 0. So those two things, together with the fact that x is symmetric, means you can write x in the following form. This equation tells you that the first two entries must be the same. So it'll look something like this. You also know it's going to be symmetric. So that tells you that's an alpha and that's an alpha. And this is a beta and a gamma. So that comes from the fact that this must be true given P looks something like that. Then you can just complete the thing. You'll end up with beta, beta, gamma, gamma, and then the remaining components are just sort of arbitrary. Epsilon, lambda, lambda, zeta. So all I've done to argue that x is of that form, use the fact that there is symmetry and that P contracted with x must vanish. Now, of course, I can work out what this combination of stuff is. Because I'm in a local inertial frame, I know that G00 is equal to minus 1, Gij is delta Ij. And if you just go through this calculation, you will discover that well, maybe I should just tell you the answer, that sigma squared is equal to, after a little bit of sweat, lambda squared plus a half of epsilon minus zeta all squared. So without making any further assumptions, this thing is positive, or possibly 0. So that tells you this term is positive, or 0. Now let's look at this term here, RAB times PAPB. From the Einstein equations, RAB PAPB for a null vector, well, you know that this is true. The Einstein equations hold. If you contract that with a null vector twice, you get RAB PAPB minus nothing is equal to 8 pi times TAB PAPB. Now think about the interpretation of the energy momentum tensor. TAB looks something like, in an orthonormal frame, energy density momentum flux and stress here. What is this combination TAB, PA, PB? Well, it's going to be energy density minus momentum flux. Sorry, plus momentum flux. Well, let's call it modulus. In general, at least in classical physics, you believe that energy densities are negative, so this thing must be positive. So RAB, PA, PB is always greater than or equal to 0. This is sometimes called the strong energy condition. And is believed to hold for all forms of classical matter. So, a consequence of that is that when you come back to look at the focusing equation, this term is positive, this term is positive. The area has got to be positive, so that tells you d2 by d lambda squared of square root of a is negative. Or possibly 0. That's why it's called the focusing equation. It tells you that gravity attracts light. If you've got any matter around, the effect is to make the light converge. This equation is at the heart of all of the singularity theorems, but I don't think that we have time to do any of the singularity theorems, so I'll just tell you that this is the key to the whole thing. Now let's go back to our black hole situation. Here we have a situation in which a black hole is sitting here in equilibrium. It gets disturbed by throwing something in, and you end up with A being different at the end, at least different in principle. In what way is it different? Well, if you think about it, there are two things that can possibly happen. Either A expands or it gets smaller. Let's suppose that it gets smaller forever. To 0. What would happen? Well, the event horizon would get smaller and smaller and smaller. The light rays would converge. So you'd have something like that, and the black hole would be squeezed out of existence at this point. You can show, but I am not going to, that the notion of a space-time manifold has to break down at this point. This point must be singular. The fact that it's singular is beyond the scope of these lectures. We can reasonably suppose that that does not happen. What then is a consequence of that? Well, This is some version of what is usually called the cosmic censorship hypothesis. It's a hypothesis because there is no proof. What then will come about if this cannot possibly happen? Well, let's suppose that we go back to this situation here, where you have some initial A. Suppose that you throw in something. Then you might suppose that our A either increases or decreases. Let's suppose that it decreases. So the first instant for which dA 1/2 by d lambda is negative is going to be here. What happens? Yes?
Excuse me. Could you explain what exactly you mean by this A, this area, in the case of black holes?
It's just the area that you would span here if you measured what the area of this surface was at fixed time. It's the area that would be spanned, just
so
geometrically.
Includes also the singularity.
Well, it does or it doesn't, depending on how you think about it. You don't want to think about the interior. You can't probe the interior. You just want to think about the exterior. And if you thought about the Schwarzschild metric, it doesn't really include the singularity. So if you thought the Schwarzschild metric was essential to what you were doing, you would look at this kind of metric. You wouldn't care what happened down here. And the area that you mean is the area as you move along the horizon there. That doesn't really contain a singularity because the singularity is always to the future. So you're talking, the area here will correspond to moving up in that direction to the future. So let's suppose that this happens at some point. You know that d2a to the 1/2 by d lambda squared is always negative or 0. So if dA to the 1/2 by d lambda is 0 at any point, you will end up with the square root of a going to 0 in some finite lambda. If you don't believe me, just draw a graph of the square root of a. Here's a picture of the square root of a. Here is lambda. Suppose that the square root of a has negative slope at some point, let's say here. You know that since the second derivative is negative, it's got to curve downwards like this. And so you'll end up at 0. If dA by d lambda is positive, that's not necessarily true. If it's positive at some point, the second derivative can always be negative, and like that does not mean that you necessarily end up at 0. So this is what happens if d by d lambda of the square root of a is negative at some point. And the second derivative is always negative, or 0. The best you can do is, of course, you see, is always have it equal to 0. If it was always equal to 0, you have a graph that looks like that. You suppose that that's not the case. If that is not the case, that tells you that d by d lambda of the square root of a must always be positive. Or 0. Otherwise, you end up with a contradiction, having a situation that looks like this. Now, let's go back to thinking about the laws of black hole mechanics. The first law of black hole mechanics was that dm is equal to kappa dA over 8 pi plus phi dq plus omega dj. And it's nice to elevate this thing to what's usually called the second law of black hole mechanics, which is that in any finite change of this type where you throw something in, dA is positive, or possibly 0. At this point, the analogy between the first and second laws of black hole mechanics and the first and second laws of thermodynamics should be immediately obvious. If the area were the entropy, this would be fine. This would look like the second law of thermodynamics, and then kappa would have to look like the temperature. So this strongly suggests the area looks like entropy and kappa looks like temperature. But in classical mechanics, you know that can't possibly be right. Here is why. Suppose you asked, what is the temperature of a black hole, and you only did classical mechanics. Well, you would stare at it and you would see no radiation coming out of it. All objects which are opaque, black holes are certainly opaque, produce thermal radiation at temperature T. And if you produce no radiation, its temperature must be 0. Since nothing can escape, that must be correct. So it looks as if the temperature is 0. Because there is no thermal radiation. That's fine unless you belong to the group of people who think there's something deeply suspicious about having 0 temperature. It is slightly more worrying when you look at the area and the entropy. If it's the case that the temperature is 0, it's not, of course, the case that dm has got to be 0 when you change something. You can keep these things constant. You just throw something in. You could change the area by some method. It would imply that the entropy must be infinite. That also seems a bit weird. But in classical mechanics, that's what happens. The remaining lectures, what I wanted to do was to show that in actual fact, there is a hidden factor of Planck's constant here. There's an h bar to the +1 in the temperature. I'm sorry. Get this right. So the resolution of this problem is that the temperature looks something like h bar times kappa, and the entropy looks something like area divided by h bar. So in the limit that h bar goes to 0, corresponding to classical mechanics, the temperature goes to 0 and the entropy goes to infinity. But in actual fact, in a realistic system where h bar is not equal to 0, that is not what happens. So the remainder of these lectures will be entirely and utterly about derivations of these two particular results and their consequences. I guess we have to stop there. So the next lecture will be on the first Thursday of next term at the unpleasant hour of 9 o'clock.